We're going to be talking about section 2.4 today, and this really goes really well with section 2.5, so I suggest if you have time to watch both of these videos together. So the key idea here that we're talking about, which again will come up in section 2.5, is this idea of a homogeneous system, right? So a homogeneous system, instead of having AX equals B, right, A times the vector X equals B, instead, we're going to have A times the vector X equals the zero vector. That's what changes. That's what makes it a homogeneous equation when we set the matrix A times the vector X equal to the zero vector. And any solutions that we find are called either trivial or non-trivial. It turns out that the vector 0 will always produce this, right? It's just like multiplying a real number times 0 to get 0, right? If I take a matrix times the 0 vector itself, then I will get the 0 vector if they're compatible dimensions, which we talked about earlier in the chapter. And we're going to be focusing on writing these solution sets, and first starting with the homogeneous case. And all we're going to do is we're going to solve the homogeneous system like we did before by using row operations to find the RREF for A. Then we're going to write the parametric form of the solution set, right? And when we do, we're going to have the solution vector X represented as a real number times a vector plus a real number times a vector plus a real number times a vector. And what the book is going to talk about is when I have three vectors, I know that the subspace that's spanned by the solution set is a three-dimensional subspace. So here we are, at least in R8, right, because we have 8 components to these vectors, at least. So when we solve in parametric form, we know that we have a three-dimensional subspace, one for each of the vectors in our solution set. And they're going to introduce this word span, which we've talked about before, but it means whatever the span of these three vectors are is the solution set. So I also want to mention that you'll find out soon this is called the null space. All possible solutions to the A times the vector X equals the zero vector, all possible solutions of that, which is equivalent, well, this is a particular example, but which is equivalent to the span of this solution set, that's called the null space. Let's take a look at MATLAB. So first, let's just do the RREF form of A. And notice that we have a pivot position here, here, and here, but notice this doesn't have any solutions. Okay, so that's kind of important, right? We're saying that, oh wait, I'm sorry. This is just, we have 3 pivots, right? So the pivots are in the first column, the second column, and the third column. And so how would we solve this linear system? Well, we'd first say that we know that, here, let me explain what I'm doing quickly. I'm sorry. So I didn't want to just take the row-reduced version of A, right? That's not what I'm solving. I'm solving the homogeneous system, which is A augmented with the zero vector. So I need to create a zero vector that has the same dimensions as a column of A, which means it needs to be a 4-dimensional vector. I don't know if you're seeing that, right? But each row of A has 4 entries, so I need a column vector that has 4 zeros in it, if I can type properly. And so now, it didn't like this. oh, I'm getting ready to multiply, but what I need is the same number of rows because I wanted to augment. So let's try this. Okay, so now it's augmented the 0 vector on here. And now I can solve this, right? Because now I know that x sub 4 equals 0 and x sub 3 equals 0. And then I have some expression for x1 and x2 that'll work. So, oops, coming down here, I can enter an equation, and I said, like we said, we know that, so x sub 1 equals minus 3/4. I'm just going to list these out. Then we know x sub 2 is free, which I'll just type in there for a second as a placeholder. I'm just trying to show you guys what's going on. Then we said that x sub 3 and x sub 4 equals 0. So here, let's just put this equation here where you can kind of see it, all right? So having come in here, right, and seeing that we know that x sub 3 and x sub 4 are both equal to 0, so we're only left with this as something interesting. So what do the solutions look like? Well, a solution x, right, is going to be a vector whose first component is, sorry, this should, let me get back in here, right, this is 3/4 times x sub 2. And x sub 2 is free, or in this case, we could say it's equal to 1. Okay. And so what vector am I looking for? Well, I'm looking for the vector that is minus 3/4, comma, 1, 0, and I'm using semicolon, not comma. Right, so let's create this vector, right, which is what we want. We want the first component to be minus 3/4 times whatever the second component is. The second component is free, and we know that these two need to be 0. And the whole hope is that we've found the vector such that when I multiply it times a, I get the 0 vector. So in terms of the book, right, we have a non-trivial solution to the homogeneous equations. Why non-trivial? Well, notice that I have a free variable and therefore was able to write an equation that wasn't just the 0 vector, right? If my only possible solution vector x was just the 0 vector, right, the one with all 0 components, then that's the trivial solution. Right? The trivial solution always exists, right? I can always multiply a times the 0 vector and get something 0, right? The question is there anything that's not the 0 vector that will serve as a solution vector for x? All right, so let's tackle the second matrix that we have here. So now my matrix B, I want to do the same thing. I want to take its reduced row echelon form after I augment B with a 0 vector. Now, there's a trick here. This 0 vector is also going to have 3 components, and I can use the zeros function, and I can tell it that I want 3 columns and, wait, sorry, 3 rows and 1 column, right? Yep, that worked, and you can see that it augmented the 0 vector on there. Why? Well, since these are all zeros to start with, none of the row operations actually change this 0. You can just row reduce A and, or excuse me, here we're doing B. You can row reduce B and then augment the 0 matrix, or you can augment the 0 matrix first and then row reduce, but you're still going to have all zeros here. Okay. And to write the solution set of this one, we have to do the same thing. And we see that we have all ones here, so I'll do it without the equation editor, right? We know that x sub 4 equals 0, and then moving up, we know that x sub 3 is free, and then we know that x sub 2 is equal to minus x sub 3, and we know that x sub 1 x sub 1 is also equal to minus x sub 3. Okay, so this is just solving. Remember, the equation has equal signs right here. So for these two, we're just moving the ones over to the other side of the equation where they're negative. Okay, so if that's the case, and that's not something I want to execute, so let me turn this into non-executable. So this is text now. Okay, so this is basically what we've learned. All right, about what x should be. So let me create that as a vector. So my vector is going to have a minus 1 semicolon, a minus 1. So these are the top two, right? That's getting the these two guys. Right now, my free variable is the one that always is going to be a 1, and then my x sub 0 needs to be a 4. Excuse me, my x sub 4 needs to be a 0. I got those numbers backwards, all right? And so now I've created this vector x, and for just a moment I'm going to, sorry. So we can see this. I just put a semicolon here so it wouldn't print out. Give me a little bit of room. And let's try it. Let's try b times x. And notice that we are in fact getting the 0 vectors. So we have found the solution set. That's a picture of all possible solutions. And let me just make the point. I don't know that it's been particularly clear, but my solution set x is equal to this vector, is equal to any scalar multiple of this vector, right? So I take minus 1, 1, and 0. And if you think about it, I'm multiplying by x sub 3, right? So the scalar x sub 3, that forces this term, the third component, to be whatever we set x equal to 3 to. And then we just make sure that x sub 2 is the opposite of that, and x sub 1 is the opposite of that. Then any vector x of this form is a solution. Okay, so that's what we mean when we talk this way. So let me get rid of some stuff here. And let's work with C just to make sure so you get one more example. Sorry. This is a 4x4, so we can use the zeros and do, we need a 4x1 0 vector to augment with C. All right. And sorry, I don't want b times x anymore. And I want to take that semicolon off so I can actually see. Okay, so here you go. Now what's our free variable? So let's just talk about how we know without looking at the, without doing the whole solutions, what do we know? Well, I know that I have 3 pivot columns. So I know that there is one free variable. One free variable when I start solving for my solution set will leave me one vector over here where I'm multiplying by one of the components of x. So this means I'm going to have a one-dimensional subspace be the solution to the homogeneous equations, right? I'm solving the homogeneous equations, and I know that the null space, which is the solution set for all possible things that can be solutions to the homogeneous equation, that's called the null set. I know that the null set is a one-dimensional subspace. All right, so again, we have so wait, x sub 4. All right, so x sub 4 is equal to 0, and x sub 3 is also equal to 0, and then we have x sub 2, which is free. And then x sub 1 equals minus 2/3 x sub 2. All right. And again, I'm going to make these text, and I'm going to put this, so now I'm looking for the vector x. I'm going to put this in, now that I've solved for these, I just need a vector x of this form. So I need a minus 2/3. I need a, let's see, the x sub 2 is 3, so that becomes a 1 in this particular vector. And then I have a 0 and a 0. And now let's try multiplying c times x. The other two worked, so hopefully the third one will. And yes, notice that here though, because we have a 4x4 matrix, right, the solution, right, the right-hand side of the equation, it's a vector that's in R4. It has 4 components, right? So we're talking about x being the set of all possible vectors that are equal to minus 2/3 in the first component, 1 in the second component, 0 in the third and fourth components. And we're just going to multiply that by the real number x sub 2, where this value x sub 2 can be any real number. I can just, any scalar times this vector. But that's the whole solution set. So I have this one-dimensional solution set. I just have this vector, right, somewhere in R4 that goes through the origin. And this vector, any point on it, will be a solution, any scalar multiple of this vector, which will just, aim in the same direction as the vector, or aim in the opposite direction of the vector, and will increase or decrease in magnitude. That is going to be my one-dimensional subspace that is a solution to the homogeneous equations. All right, so you should definitely take a look at the textbook in section 2.4 and try to understand what they're talking about. I do want to mention one final thing, which I just went over, the dimension of the solution set here, right? When there is one free variable and the system is consistent, right? We can't have 0, 0, 0, 1 in the bottom, in the last row, right, where we have an inconsistent reduced row echelon form. But if we have a consistent reduced row echelon form, then we have one free variable. That means the solution set is a line, or as I was saying, it's the vector, all the points on the vector. And when there are two free variables, the solution set is a plane, right? So knowing how many free variables there are will tell us how many dimensions this solution set has, which is the null space. The null space, when I have one free variable, has one dimension, and the null space has 2 dimensions when I have 2 free variables. And if I were to have 3 free variables, then the null space would have dimension 3. And they're also going to talk about the difference here. I'll just say that we have 3 kinds of spaces. We have the column space, which is the span of the columns of A. We have the null space, which is all the solutions to the homogeneous equations, right? So the solutions to this is my null space, the solution set. And then we also have the span of all the rows of A, which is called the row space. And they're trying to make sure that you don't get the column space confused with the solutions to the homogeneous equations, which form the solution set for the null space. So definitely read the section 2.4 there, and definitely consider also looking at section 2.5 along with it, because we can use these ideas about span and solution sets to determine whether or not a set of vectors is linearly independent.